Hello, how's everybody doing today? I hope everybody had a great lunch, both here in San Francisco and online. If you haven't had lunch yet, I hope you're eating while you're listening to me because that'll make it slightly more entertaining, but I'm gonna try to entertain you nonetheless. As you can see, we have two names up here. I'm half of those names. My name is Stephen Dang. I've been at Uber for a little over 2.5 years now. And Prasad will be coming up right after me. So thank you for having us. I guess, Ryan, thank you for agreeing to have me on my team. Okay, so what's happening today? Okay, so we are going to kind of give a small overview of how Uber manages a lot of scale for our SPIFFE SPIRE deployment, and we're going to tell you about how we've had a couple of performance improvement gains and contributions and how they contribute to our giant scale and our giant price tag that we like to run up as a cost center. I know everybody here knows what a cost center is because we're the biggest ones, aren't we? Okay, so while making this slide, it definitely felt a little like I was doing an interview for a new candidate for my team and saying, hey, you should scale this to unfathomable amounts, and oh, these numbers are never going to happen, but these numbers actually do happen at Uber, and I'm sure at many other companies. But this is kind of one of the first times I've kind of put it down on paper and said, wow, that's pretty cool. Well, Uber does 25 million trips a day, give or take. We are global, all around the world. Everybody knows what Uber Eats is. You probably eat it before. We have 300,000 hosts globally, ranging from on cloud, on prem, yada yada yada. We have many different types of EC2 containers and things like that. But the important gist of that is with that many hosts and the scale that Uber operates at, we have approximately 5 to 6 million containers, and that number is always rising, actively running at any given time. That's not including down containers and services that get turned down and things like that. By end of year-ish, beginning of next year, we expect to have anywhere between 15 to 20 million unique SPIFFE IDs running at the company. Okay, so what does that actually mean other than just some numbers on the screen? With so many hosts, so many containers, so many IDs, so many different IDs, and so many agents and servers running worldwide, we need to ensure at Uber that we are not running up that cost center that my manager is looking at me right now. Stop talking about cost centers. Every small picobyte of memory or CPU utilization that we can reduce is saving money towards the company. If a small thought experiment, if say your SPIRE agent is running on every host, right? At 300,000 machines, say you're running at 2 gigs of memory, you reduce it by half a gig of memory, that's 150,000 gigs of memory reduced, like that, just for that one tiny little agent or running on every host, right? So that's boom, 150,000 gigs. So with that, we also have, we can talk about scale from the perspective of performance. We can also talk about scale from the perspective of security. For the next two things, they go very hand in hand, as I'm sure you're all aware. When SPIRE agent is looking for the authorized entries of the workloads that it's responsible for, right? It's pulling everything that's parented to it or that it's responsible for. How we model and how you model the topology of your entries, what it's parented to, affects it so much. Related to the first pillar here, the more workloads that every agent is responsible for, not only is it a security risk, right, but it's also increasing that memory footprint a little more. And let's say a third of those machines has a couple hundred or a couple thousand extra entries, those numbers really add up over time. Does it really matter other than cost? Yeah, actually. At Uber, we have we've coined a new term called identity propagation delay, IPD for short. That we somehow keep bringing up in conversation probably once a day or once a week, or maybe just Prasad and I talk about it way too much over lunch. But what does that actually mean for us? Identity propagation delay. We break it down into 4 very, very large pillars, and there are many smaller pillars that make up each of them. At the very top of it, at the very beginning, container schedulers. So if you're using something like Peloton or Kubernetes or something like that, how long it takes for whatever you're using to register those containers or those IDs to Spire server, it's never like that, right? It's always like that. It's a little longer, a couple seconds, couple minutes, right? That delay is super important for many reasons. We also have registration delays. That thing that's actually making those calls to Spire server, it's not going to be instantaneous. It could be pretty instantaneous. It hopefully is, but it's not. It's latency that we have to account for. Okay, now here's the big one, at least for our team. Spire server cache syncing. Okay, Spire server cache syncing. One of our Spire servers or Spire DBs has anywhere between 50,000 to 1 million entries in its database at any given time. When Spire server wants to rehydrate that cache, the larger that database is, the longer that connection takes, and the longer it takes to rehydrate that cache, the older and staler your data is, which that's not anything we want. You never want anything stale, whether it's your lunch that you had today or whether it's the cache that you're syncing, right? And then the last thing is Spire Agent syncing, as we just talked about. Spire Agent syncing, as it syncs down its authorized entries, all these things from very top to very bottom, if you can get it down to a couple seconds, oh my gosh, you are absolutely golden. Realistically, for our scale, we don't do that. We can't do that. So this is kind of talking about all those problems. And I kind of want to talk to you about like one specific case study that happened to us recently, where this scale just kind of blew up. Okay. So we all know what Spire server is. We all know what Spire agents are. More often than not, you have a couple of Spire servers running. You have many Spire agents running in a very heterogeneous environment. And usually, you have many more Spire agents to Spire servers, correct? Maybe? Yes? Nod? Yes? Nod? No? Okay. What happens if someone decides, I don't know, networking decides, hey, we can't handle, something blipped. Small blip in the universe, and all your Spire agents can't talk to Spire server. Ooh, that's fun, that's fun. Well, every Spire agent in the world, or at least at Uber, or at least maybe in the zone or something like that, can no longer talk to Spire server. And that's a lot of people playing telephone with like 4 telephones at the same time. So what happens? Our on-call can't manage that. We have a lot of Spire, we have cascading failures of lots and lots of Spire agents. So we have thousands or hundreds of thousands of Spire agents trying to reattest and trying to start up to a Spire server that's also trying to start up and rehydrate its cache, and no one has any information. It's like the latest gossip just came out, and you really want to know what's going on, but no one knows what's going on, but you really need to know. So what ended up happening was we had hundreds of thousands of Spire agents trying to attest. Spire servers trying to rehydrate cache. It's taking hundreds of thousands of connections all at the same time, and ooming or out of CPU, or it just can't process all of it. So what happens? Spire server goes down, Spire agents go down, and we just keep going and going and going. You're like cycling in a track. You're like a little track runner, right? So what we ended up having to do because of this massive scale is very slowly let the Spire agents come in. So at least for Uber, we had, rather than like allowing everything to come up very gracefully, we had to say, hey, single file line, come one at a time. And that's just one of the things that has happened. I'm going to bring up Prasad to talk about some improvements that we've made recently and how we've reduced that cost that we keep incurring, just a little bit.
Thank you, Stephen. It's always tough to follow Stephen. I think this is second time I should go first next time. But yeah, so the next thing we're going to talk about is SPIRE Agent LRU Cache. I'll give you a little bit background on this. So Steven mentioned we have a high memory footprint. So the way our topology works is we were like one of the first adopter of SPIRE. So reliability was very important for us. So that's why we register workloads instead of hosts to a cluster. So what that means is agent is responsible for thousands of SWITs. So basically all the workloads in the cluster. So as we started scaling up, as number of workloads in a cluster started going up, the agent, we started agents causing out of memory traps. So this was bad. And one of the reasons for the memory consumption at the SPIRE agent is SPIRE agent caches all the SWITs. And the reason for that is if you connection to the SPIRE server for some reason drops for a few hours or a few minutes, then you don't want that to affect to the workloads. That's why all the SWITs are cached in agent. Now this was a typical cache, but because we had so many SWITs, we wanted something like LRU. It's a typical LRU cache, but it has some more additional, like 3 of these extra abilities. So I'll go over one on one. So first one is during the startup, we fill the cache. So the way this helps is if any agent that is managing less than number of cache size of entries, it will not see the negative effect of cache misses. All the SWITs will be cached for them. All the workloads will enjoy the high reliability. Second thing we do is all the active subscribers, which means all the workloads that are actively calling to workload API and getting SWITs, they are all always persisted. Doesn't matter if it goes above the cache size because we want them to continue to have SWIT even if server goes down. And the third thing we do is we have faster sync interval if the cache misses are mainly for the active subscriber. What it means is agent and sync currently has default 5 seconds of interval. So every 5 seconds it's going to get authorized entries and then it's going to get signings for those SWITs. And it's a periodic task. So if the new workload that comes in, because of LRU cache, there will be cache misses. So it shouldn't have to wait 5 seconds or whatever default that you are setting. So we created a new faster periodic sync, which runs, I think, 500 milliseconds. And it looks for all active subscribers which are waiting for SWIT and gives them SWIT. So with these 3 changes, which are actually running in our production for past few months, and we've seen some significant performance gains. The first, again, we've seen is the main motivation for this was reducing the memory footprint of SPIRE agent. So we've seen some significant gain there. As we keep on reducing the cache size, I think we can reduce our memory to half, even more than half of what we have allocated. Second thing is, because we are not asking for every SWIT signing, agent is not asking for that, which means server has to do less signings. So that has reduced the load on SPIRE server as well. This was a pleasant surprise to us, but this is a significant less CPU load on the server. Third one again is SPIRE agent startup. At the startup, agent fills its cache with SWIT. If it has less SWITs it's managing, then it's faster time up. So we have seen that also, and it helps especially when you're doing the SPIRE server, SPIRE agent deployment. If the workload is asking for a SWIT during the deployment, it has to wait. If the startup time is less, then it has to wait less. So less noise, our on-calls can enjoy it. And then the fourth one is no significant impact on the first identity or cache miss cases, because we added that second periodic sync which runs faster, like every 500 milliseconds. The cache misses were served pretty quickly, so within a second or so, on an average, we are seeing the workloads are able to get identity. So, and then, yeah, like I said, SPIRE server CPU usage, as we are reducing the SWIT cache size, it's reduced to almost 40% now. So that was a very pleasant graph for us. And with that, like Steven mentioned, we have a couple of things we still want them to be able to work at the scale we are. First one is I think it was talked about in the project updates as well. We are working on this events table fix, Faisal is working on that. So we are really looking forward to that fix. That's going to help us reduce the identity propagation delay. That's very significant for us and will unlock various use cases. So we are very keen to take that fix. And then second one is the scenario that Stephen mentioned where Spire server kind of went into that spiral. We would want some solution to address that. One of them could be having a throttling strategy, which we may currently not have. So that is the second thing. Uber would be happy to look into that, what we can do there. But yeah, these would be the two things we are very looking forward to the next. And that's it. Thank you from me and Stephen. If you guys have any questions.
I have a question related to what do you do with memory that's you free from SPIRE Agent. Let's say it was used like 100 megabytes for a node. Now it's used 50. What do you do with the 50 megabytes?
So we run agent as a systemd. So if we just reduce it, then we give it back to the host. And then maybe compute can use that extra memory.
You mentioned identity propagation delay being a persistent headache. I'm curious to hear you or your co-presenter elaborate a little bit on the kinds of problems you've seen it caused, and also what you do to manage and deal with it, if anything.
Yeah. So main thing is when the new workload, let's say scheduled, a stateless service is scheduled, then it has to wait for identity before it starts its outbound calls, otherwise they're going to fail. So there are two cases, should you wait or should you not wait? So addressing that challenge, it has to be case by case basis. And second thing is we have our libraries. So whatever timeout we have specified in those libraries, if IPD goes beyond that, which means that workload is getting crashed. So then it's going to crash loop, not necessarily crash loop, but at least go down once until it comes up second time. And if it's coming up on second host, it may happen again. So this will be a headache both for someone who's schedulers and for us. So we want that to be as low as possible.
And to expand on that a little, I think that like philosophically, we operate with authentication almost as a pseudo health check. So if you took the band of, oh, we don't care about identity, that's fine. Most services should care about identity as it's waiting for that first identity to be received from the propagation delay. We're using up resources that is very costly to the company. And we're also probably giving false positives that if that identity never gets there for some odd reason, then that service really isn't healthy. So it's kind of turtles all the way down, where we're giving false positives, we're giving false signals. We need to get it to there as fast as possible, or we're just using up resources for 6 million containers. Awesome, thank you.
I think there are some questions in a chat, at least 2 or 3.
Do you guys use JOT SPIDs? And if so, have you noticed any degradation in bundle propagation in larger developments?
Yeah, so our bundles are managed by a separate service, and those live in cloud. So those rarely change. So we haven't seen any degradation with that. And in terms of JOT SWIDs, we use Xfine and SWIDs, and then we use JOT, which is like our format, Uber format, built on top of it. And those are short-lived, I think 5 minutes. Those are injected into outbound calls.
I think, do you have any matrices around cache hit rates in the agent side cache?
Could you repeat that?
Do you have any matrices around cache hit rates in the agent side cache? Curious if those changed as you have adjusted the agent side cache size?
Yeah, I have to go back and check, but currently we have cache size I think of around 2,000 or something, and we haven't seen any significant impact, or at least some complaints where it is causing problem for workloads to get identity because of this cache misses. So yeah, I have to check if we have added metrics in upstream SPIRE agent for that. Probably we should. Yeah.
Is the cache miss blocking for the workload? Got it. Does that help at all with your identity propagation delay problem?
It does not help.
It does.
Cool.
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 Thank you all.
Thank you.
Thank you.
I think with that,